All right, if you have a function that alternates, and you will be able to tell because you will have this alternating component right here. It comes in a couple different forms. It's -1 to the n, or perhaps -1 to the n plus 1, or maybe even -1 to the n minus 1. I kind of refer to that as a blinker light. What it does is, if n is 1, and you were to plug a 1 in here, it'd be -1. But the moment n becomes 2 and you're plugging a 2 in, it's +1, and it goes back and forth. And so that makes the series alternate signs. So it's called an alternating series. Alternating series will converge if the following two conditions are met. Condition number 1, the limit as n approaches infinity of a sub n is 0. Let me be clear here that a sub n is the part of the summand that is the non-alternating part. Okay, you've got this alternating component ahead of it, but a sub n is the rest without the blinker light, if you will. If that part is heading towards 0, then it's possible that this is an AST. The second stipulation is that the a sub n part of this is decreasing, or at least not increasing. It's staying the same or getting smaller all the time. Let's check out number 1 and we'll see what we have. So determine the convergence or divergence of the series. So I'm going along a big homework set and suddenly I see this. I'm like, ooh, alternating component, blinker light. This is going back and forth between positive and negative, so it might be an AST problem. Let me look at the rest of it. And the rest of it, without the alternating component, is 1 over 2n. Now I have to apply the test to that. Is the 1 over 2n heading towards 0 as n approaches infinity? When I start putting 1s, 2s, 3s in here, is it heading towards 0? And the answer is yes, it is. All right, case number 2 is a sub 2 less than or equal to a sub 1? Or is a sub 3 less than or equal to a sub 2? In other words, is this 1 over 2n getting smaller all the time? And again, the answer is yes, it is. And you don't have to take a derivative, by the way, like we had to with the integral test, thank goodness. So yes, this checks off both prerequisites, number 1 and number 2. So therefore, we can say this series converges because of AST. Okay, number 2, immediately this catches my eye. I'm like, okay, this might be alternate. Well, it is alternating. It might be an alternating series test. It might converge. By the way, AST is a convergence-only test. Okay, if the two conditions are not met, it doesn't mean it diverges, it just means we don't know. Once again, the a sub n is the rest of it, not including that green alternating component. We have two things that we have to decide. Is a sub n heading towards 0 as n grows larger, as n becomes infinity? Is that heading towards 0? And the answer is no, it is not. It's heading towards 1/4. And so therefore it's not going to be an AST question. Well, now if we can't use AST, what do we use? And generally the answer is nth term test. The nth term test says if the entire thing is not heading towards 0, it automatically diverges, which is what's going to happen here. Now the nth term test isn't just a sub n. The nth term test would have to let the blinker light back in. But this is simultaneously heading towards positive 1/4 and negative 1/4 as you get out near infinity. It's wildly oscillating is the term that we use. If you're heading towards either 1/4 or negative 1/4, you're not going to end up at 0. So this diverges by the nth term test. I'm going to write out a full out answer that looks impressive. All right, there's a well-written sentence that describes my situation. So that's number 2. Number 3, I see the alternating component. I think, okay, this might be AST. If you look at the rest of it, which of course will be 1 over n to the 1/4 power, that's the A sub n. A sub n has 2 prerequisite tests to meet before we can claim AST on this. Is it heading towards 0 as n gets very large, as n heads out towards infinity? And the answer is yes, it does. It becomes 1 over infinity, that will be 0. So you can check that one off. And secondly, is it decreasing term by term? When you put in a 1, then a 2, then a 3, is it getting smaller every time, that blue part? And the answer is yes, it is. So this series converges by AST. An interesting side note, if the alternating component was not there, this would have diverged. It would have been a diverging p-series. So the fact that we were going back and forth and changing signs actually made this add up to something instead of adding up to infinity. Interesting. And it should sort of make sense that going back and forth between positive and negative would sort of tame this a little bit, make it not so wild and crazy. So, all right. Now, one final note before I move on to number 4. Even though I know it converges, I can't figure out the answer. I can't figure out what this adds up to without the help of technology. That's why I showed you the screenshots from section 9.2. So if you wanted to add up the first 1,000 terms of this thing, you could do that on your calculator. The only 2 tests that we know where you can actually figure out what something adds up to would be geometric. Remember, that's term 1 over 1 minus r, and telescoping. Otherwise, you can only tell whether a series converges or diverges. Number 4, there's definitely an alternating component. I look at the rest of it, the n over natural log of n plus 1, and I realize that since n grows at a normal rate and natural log grows much more slowly, the rest of the fraction is going to get larger and larger and larger, which means this is not heading towards 0. Therefore, the AST fails, and this is going to diverge by the nth term test. This is another example of something that oscillates. This is a really clever problem because it doesn't look like an alternating series, but it absolutely is. If you take a 1 and plug it in for the n, here and here, up top you get the cosine of 1 pi. Well, cosine of pi is negative 1. And obviously 1 squared. Plus, because it's a sum, let me put a bunch of pluses here. If you make n equal to 2, up top in the numerator, you're going to have the cosine of 2 pi. Well, the cosine of 2 pi is back to 1. The cosine of 3 pi would be negative 1. The cosine of 4 pi would be 1. And so actually this is going to produce an alternating series. Oh my gosh. Interesting. So since you do have a blinker light, even though it didn't really explicitly appear in the formula, it absolutely is. You can rewrite this original summand if you want to. I think I will. Okay, what I just did is not mandatory, and it is optional, but I wanted to do it as a teachable moment. So now you can look at it and say, can I use AST? All right, if we look at A sub n, which is, of course, 1 over n squared, let's see if it obeys the 2 rules that it needs to for AST. Is it heading towards 0 as n approaches infinity? And you can see that it is. And secondly, is it getting smaller? At least, is it less than or equal to the term ahead of it? Well, yeah, it actually is decreasing the whole way. When you put a 1, 2, 3 in there, it's getting smaller. 1/2, 1/9, 1/16. So this converges by AST. All right, this will be the last one for day one. I went back to the textbook. They've got an awesome example. Occasionally, a series can have both positive and negative terms, but not alternate. Let's investigate what they gave us. They gave us the sum of sine of n over n squared. I went ahead and wrote it out, at least the first three terms, plugging in n's. But if you look at this, the sine of 1, the sine of 2, and the sine of 3, remember 1, 2, and 3 are in radians, would put you up here in either quadrant 1 or quadrant 2. Remember, when you're doing radians, when you go all the way to pi, 180 degrees is pi radians. That's 3.14. So 3 radians is still just barely going to keep you in quadrant 2. So the first 3 terms are all positives. The moment you do sine of 4 over 16, you're going to go into quadrant 3 and you're going to go negative. And the next 3 will be negative. So it's changing signs but not alternating. In fact, it won't even go in multiples of 3 because, pi is an irrational number. So this isn't alternating. So how can we tell? How can we make it either converge or diverge? This is intriguing. And the answer to our dilemma is the squeeze theorem or the sandwich theorem. All right, here's my setup for the squeeze theorem. We know that sine of anything has to stay between 1 and negative 1. So the entire blue summation would have to stay between the red and the green summations. But red and green are both converging p-series from earlier in the chapter. And since they both converge, and blue has to stay between them, blue will also converge. So we figured that out by using a combination of squeeze theorem and p-series. All right, that's all I have for day number 1 of the alternating series test, AST. A quick summary. The AST can be used if you see an alternating component, like a negative 1 to the n or negative 1 to the n plus 1. If you do, then the rest of the summand becomes what we call a sub n. If a sub n is heading towards 0 as n grows large, and if the terms are getting smaller, then the sum converges by AST. That's it. All right, we'll see you guys next for day number 2.